Yeah. So while people are joining, I would like to yeah, start already a bit. Yeah, welcome you to this afternoon session in our webinar series, which is hosted by the European Microwave Association, EuMA. And today with me here is Nicole Vorhauer-Huget, who's with Magdeburg University, and I will introduce her in a few seconds right before the time. Yeah, welcome also from me. So my name is Jan Marowski. I'm with Bochum University. I have the pleasure to host this session today. And yeah, before we start with Nicole's talk, I would like to take the chance yeah, to show you some of our slides, some of our activities that hopefully are interesting to you. So as said before, our today's speaker is Nicole, who will give a talk on the use of microwaves for process engineering applications. Nicole is with the Otto von Guericke University as a research group leader. Yeah, if you are interested in the other installments and events of our webinar series, you can just follow us on LinkedIn or visit our YouTube channel, which is also provided by this QR code here if you're interested. So there's quite a wide range of talks available by now. So we've had sustainability topics, we had classical engineering topics like phased arrays and antenna developments, channel models for communication systems, and so on. So yeah, if you have the chance, it would be great to look around there. Yeah, as the year is already continuing into summer, I'd like to take the chance to do some advertisements for the European Microwave Week, which is our major event in usually fall each year. So this year, the Microwave Week will take place from 21 to 26 of September and hosts 3 microwave-related conferences in parallel: the EuMIC, the European Microwave Integrated Circuit Conference, the UMC, the European Microwave Conference, and the EuRAD, the European Radar Conference. So there's a whole bunch of scientific talks. It's a great chance to network. And also for those of you who are graduate or undergraduate students, there are also pretty neat opportunities. For example, our microelectronics school, our radar school, our microwave technology schools as well. There is a young professional event and a career platform. If you'd like to take the chance to network with potential industry partners, come and join us there. We will be in the Netherlands, in Utrecht this year, and I'm sure it will be a great event. Particular for those of you who are students, we have this volunteer program. So you can join us there basically for free in exchange for some work. So if you are available to help out a bit on different organizational topics, batch scanning, these things, you can help us out in organizing the conference for 2 or 3 days, and then in exchange have full access to all the conference technical sessions, to the huge industry exhibition, and some more benefits like a hostel stay, lunch on the duty days, and so on. So take the chance to look at this. Application deadline is already approaching, so it will be June 1st. Yeah. Okay. And now I'm done with the ad block. I have the pleasure now to introduce to you Nicole Vorhauer-Huget, who is a postdoctoral researcher at Otto von Guericke University in Magdeburg, Germany. Nicole completed her binational PhD in process engineering at the National Polytechnique de Toulouse in France and at Otto von Guericke University in Magdeburg in 2018. And since then, she's a group leader at the Group of Transport and Porous Media in Magdeburg. She's an academic editor for the Wiley Journal, International Journal on Chemical Engineering, and the University of Liège recognized her work by a Woman in Drying Research Award in 2017. Nicole received the Maria Weber Grant in 2020 and the Young Drying Scientist Award at the 23rd International Drying Symposium in Wuxi, China. Her research is mainly related in inoperando imaging and pore-scale modeling of coupled heat and mass transfer related to drying, freeze drying, microwave heating, which is of special importance today, water electrolysis, and productive biofilms or pyrolysis. And with this, Nicole, I'm very happy to have you here. And yeah, the stage is yours.
Thank you, Jan, for this very kind introduction. And thank you, EuMA, for the invitation for this webinar. I'm very happy to be here, although you will see my background is quite different maybe than of the previous speakers. But let us see. I will share my presentation. So hopefully you can now see the presentation.
Yeah, we can see it.
You can see it, and I will also try to look in parallel on the Zoom just to know if there is something happening in between. Okay, good. And you can also see my pointer. Yes, right. So this introduction has already been made, and maybe a little bit more to the research background. As you have already heard, I'm a process engineer. And as you can see from these pictures here, microwave heating plays a big role in our research, and that's why I was invited by Jan to this webinar to see what is maybe the overlap or what are common interests that we follow. Besides of that, we are also simulating heat and mass transfer for many different other processes, also experimental studies, material analysis, and microfluidics. We do also for other applications, and these other applications Jan has already mentioned is, for example, PEM water electrolysis and freeze drying, so completely different topics. You can find out more about these details on our website. I don't want to go too much in detail here. The time would not be sufficient to cover all of it today. Maybe to get you or to take you from somewhere. I mean, as an electrical engineer, there's a little bit maybe a big gap in knowing what is process engineering is a completely different topic. But I guess what you know already is that process engineering is very much related to chemical production. As you can see here, a big chemical site, a chemical production site with many different processes taking place. But it's also involved in pharmaceutical production, food production, or production of construction materials. So our everyday life is very, very much affected by process engineering. And especially for the upcoming task and importance of, for example, circular economy with the future goals of climate change and such things. Of course, process engineering makes a very big contribution here. But also to sustainable energy supply. So, for example, fuel cells, water electrolyzers. This is also process engineering, among many other things. One could briefly say that process engineering is actually the conversion of mass and heat, by the way. So this means the substances, their composition, their type, their properties is converted from one type into another type by physical, chemical, or biological processes even. And the heat actually is also converted, because usually we convert the heat into a chemical reaction or a phase change or something different. So this is process engineering. So not that bad to learn it within a few minutes, I would say. And maybe to give you an example, which looks very simple on the first sight, but is maybe not so simple if you look a little bit deeper into it, is drying. So drying is the removal of water using thermal energy, also using heat, and is something that we daily experience. So for example, in the morning, when we blow the hair to get it dry after shower. This is the drying process. And here in this case, we use, as I said, the hot air to evaporate the water and to remove the water actually from the hairs and to transport it in vapor form to the environment. And there's also drying, for example, of clothes. It's a little bit different heat supply. So when we use hot air here with the hair blower, in the other case, it's a hot shelf that transfers the heat actually to the wet solid for the evaporation. So the conversion here is the phase change of water from liquid to vapor. I think this is easy to understand. The heat transfer here is by hot air or contact to a hot shelf to the wet solid. And the mass transfer is the transfer of the evaporated water into the surrounding. And now we come to microwave, application of microwaves, and related to the topic shown on the previous slide, to drying, I would like to point out at the beginning of this presentation on microwave drying. Microwave drying is well established in food industry to dry fruits or food additives. It's also established in pharmaceutical production or production of pharmaceuticals or biopharmaceuticals. So I've collected here some pictures from the internet to highlight the applications of microwave drying. So we have here actually microwave freeze drying. So this means it takes place at a very low temperature and usually also low pressure, but also at ambient pressure and a little bit higher temperatures. What you can see here, what is very important to understand is that the products have a very different properties. So they can either be bulks. So for example, here in microwave freeze drying, the solids would be frozen on block. But it can also be particles that are treated. We can have relatively small product and particle size as the powder that we see here, or we can even have a combination of this microwave drying technology with other technologies, as I said, for example, in vacuum freeze drying, or for example, here in the extrudation process, microwaves could also be included to enhance the process. Other examples are the microwave drying of building materials. So for example, of wood, of ceramics, or even of foams, of wrapping materials, or even electronic devices. I've put here image of a microwave wood dryer. This is a sink that we have dried actually at our institute. This is a paper that is used a paper carton that is used to protect materials. This is some form that we use to make some shapes of other products that we would need later on. And this is, for example, a foam. So again, here, the thing to recognize is that we have a big scale transition from small particles to relatively large and thick materials. We have complex geometries, especially with grooves, that are not possible to dry or hard to dry with other technologies. And even highly porous materials can be dried with microwaves. So there are quite a lot applications for microwave drying. And why is it so interesting to do research on that? If there are already industrial processes established, why are we nowadays looking that much on the application of microwaves? This has something to do with the European Green Deal, which has the high goal to achieve GHG neutrality in 2050. In Germany, we even put the goal to achieve this in 2045, and Bavaria in Germany even 5 years earlier. So this is very tough. And for this, we need, of course, new technologies and new production pathways. And when you look today on our website, on the OVGU website, our university website, you find actually a picture of a microwave reactor. And you can read the text out there, and I have highlighted some of the most important things here. Why are we using it? Why are we interested in that? It is one option to achieve sustainable production. We can use renewable energy sources because it's actually an electrified process. This can decarbonize the energy supply. Due to the volumetric heating, we achieve a higher energy efficiency. This is what we understand as process intensification. And there are other things that are even important, like better process control, different process conditions, tailored product properties. So this is motivating actually our research at the moment. And before we go into this research topic, to give you also maybe a broader understanding of the process engineering point of view, I would like to give some introduction to what is defossilization, what is decarbonization, and how microwaves are supporting actually these goals of the European EU Green Deal. So in chemical industry, actually, when we talk about defossilization or decarbonization, we usually talk about the material aspect. So we would like to remove all the carbons, maybe the fossil-based products by new sustainable and maybe products that are even recycled in the circular economy. But for microwave heating, I'm talking today about the substitution of energy carriers for process heat. So this means that all the processes that take place in all these process engineering applications, chemical production, and so on, they need heat for the mass conversion, and this heat can be, of course, so is now at the moment provided by or based on fossil fuels, and this could be based on electrified processes, and microwaves could be one option here. So maybe to give also the definitions here, decarbonization means we get rid of all of the carbons, all of the Cs, CO2, CO, and so on, out of the process. And I think for heat supply, this is pretty much realistic. So this means we don't burn any fossil fuels anymore, and we base the heat supply completely on renewable electrical or electrified energy sources. Defossilization, in contrast, means that we cannot remove the C from the processes. There's some carbon always. Many products in chemical engineering are based on carbon, but that we recycle the carbon actually so that the CO2 concentration in the atmosphere is not further increased. Energy is a very important topic, and in Germany, at least in 2020, 19% of the total energy consumption in Germany was used for the process heat. So you can see here, this is the industrial sector, this is the process heat. So it's 440 terawatt hours in 2020. And you can see by that time, there was only a very tiny part based on renewable energy sources, namely only this green part here. And some part was based on electricity, but the electricity was not generated by renewable sources. So this is a very big, a very huge amount compared to the overall energy consumption in Germany. And when you look a little bit closer, you can see that most of the energy is then used for processes above 400 degrees Celsius, so for high temperature processes, but also that the processes that take place at lower temperatures, of course, also have a quite significant energy consumption. And when I come back to drying, which is a process that takes place below 100 degrees Celsius, so this is here almost 1/4 of the circle. So it's quite important to look at this energy consumption. And then the point would be, if we are thinking about electrification of process engineering, and if we are thinking about GHG neutrality, then we cannot achieve this when the energy consumption increases. So what we have to do in parallel to the replacement of the fossil fuel burning or the fossil fuel-based process engineering or industry is to decrease significantly this energy consumption. And in Germany, there is the EuMA. It's quite a big organization for the chemical industry, and they have written a roadmap for 2050 because of this European Green Deal. And they make some suggestions on how to reduce this energy consumption. Some suggestions I would like to read out here. So for example, what would be possible is to substitute state-of-the-art processes by other approaches that are, of course, less energy intensive. Reduction of temperature levels would be one option where it is possible. It's not always the case. The avoidance of heat loss through insulation. I mean, this is somehow obvious and is, of course, done where appropriate. The use of heat cascade utilization so that we also avoid too much heat losses along the process chain, or also these heat pumps are other examples. And one point that I would like to highlight today is actually the process intensification. So this means to make the processes much, much faster with a much higher throughput so that the energy that is required per kilogram of produced material is significantly reduced. And for this process intensification, there are, based on electrified technologies, there are 3 options that are mentioned in this roadmap because they are electrifiable. And this is direct and indirect resistance. So that means ohmic heating. This is induction, and this is microwave heating. And I would like to point out or to focus today only on the microwave heating for obvious reasons. What are the advantages of microwave heating? I mean, I think most of you know, but let me go through that still quickly. So it's you have the possibility for direct volumetric heating. Based on that, there's at least expected high energy efficiency, and only the product is heated, and the reactor room or everything around it does not have to be heated. It has very high heating rates if the material allows that. This means we can achieve reduced process time and high material flow rates. For chemical engineering or process engineering applications, it's also interesting that the temperature gradients are inversed. So I think from the home, you know, if you heat something in the oven, the heat will be transported from outside to inside. So the temperature gradient is from hot surface to cold core, at least at the beginning of the process. In microwave heating, it's the other way around. It's a hot core and a cold surface. So this means that the reaction products that might be produced inside of a material that is undergoing a chemical reaction are transported in opposite direction to the temperature gradient than in conventional processes. This can result in improved reaction conditions. Also endothermic reactions in which the byproducts are otherwise burned can achieve a higher efficiency because the burning would not be necessary anymore. And this would also mean that we don't need oxygen in the process, which can have significant advantages for certain processes. I have put here some examples for the processes in which microwave heating can be applied otherwise than drying. About drying we have talked already, but other applications would be crystallization, melting, pyrolysis, sintering, a reduction of iron, or the direct reduction of solar silicon. And as you can see, the temperature levels at which microwave heating can be applied are also covering the full range of the levels that I had shown you before. So this is quite interesting. But every process that has a list of advantages can also come along with a list of disadvantages. This is clear. So for microwave heating, the disadvantages are actually the dependence of the heating, of the efficiency, of the heating rates, on the loss, so-called loss factor of the material. This limits microwave heating in application for certain materials. So for example, the pyrolysis of plastic with microwaves would be problematic. And then very often susceptors would be required. The dependence of heating on the geometry is something that I would like to point out clearly today. I will show you some examples. And this can, of course, also lead to size limitations. And then the scale up, which means I increase the product size from something small to something big, can be problematic. The risk of local overheating, especially in thermally thick products, is a big disadvantage. I've brought here some image from Actually, this is clay sample, and you can see the brighter parts here in the center. They are dry, so there's no water anymore. The darker parts still contain water, and obviously there was a local overheating because we have evaporated here the water or pushed out the water here from these spots. While the other parts remained wet, and this is of course a problem in process control. Yeah, so the temperature gradients are reversed. They're high in temperatures high in the center, and this if the heat transfer is limited, can be very problematic. And of course, the leakage of any EM field is also problematic, so the reactor design must take this into account. This means from the process engineering point of view, it is not at all possible to use the apparatuses that are currently established and just equip them with a solid state generator or magnetron or whatever. It means that the complete design of the reactor needs to be renewed. Now, yeah, this is something that you know. Microwaves are high-frequency electromagnetic waves. What is interesting for the talk today is that we use only ISM frequencies, so industry, science, and medical frequencies at 915 and 2450 megahertz in Germany. These are the allowed frequencies for processes. And of course, the heating is based for water, for example, on the asymmetric molecule structure. Yeah, so for the orientation polarization of the dipole, so the dipole rotation of water, which is quite interesting for water-containing products. Yeah, so as for example in drying. Can be also based on electron conduction or, of course, on ionic polarization. Drying takes place usually at temperatures well below 300 degrees Celsius, so water is then evaporated and in vapor phase at this temperature, definitely. And at higher temperatures, for example, for ceramics, other processes start to play a role, and electronic conduction maybe. If we think about carbonization, for example, can be done even at much higher temperatures. We will see later. I would like to give you a very short introduction to again to the heat transfer condition, because this is important for the understanding. The conventional heating process, as it is realized in an oven that is operated with hot gas, there we have the heat transfer actually from the center of the hot gas to the surface of the solid. And then there is heat conduction, thermal conduction from the surface of the solid into the core of the solid, where the reaction, the phase change or whatever can take place. We can calculate the transferred amount of energy with a very simple equation. So K in this means the heat transfer coefficient. A is actually the surface area, and delta T is the temperature gradient between the hot side and the cold side, or between the hot spot and the cold spot. And as we have here a parallel or a series, connection of heat transfer resistances, the K is also combined of the thermal conductivity in the gas phase, the heat transfer coefficient in the gas phase, and the thermal conductivity lambda in the solid. Yeah, and what is important to understand is that the heat transfer coefficient alpha, I come back to this picture of this hot gas drying, is depending on the geometry of the material and the flow conditions of the hot air. The thermal conductivity lambda is depending on the material property, so on the internal or on the intrinsic property of the material where we would like to conduct the heat. And there are big differences depending on the material. Water is, well, conducting heat not so well, while steel is conducting heat very well. And additionally, the thickness of the material plays a role. Of course, the thicker it gets, the longer I need to transfer the heat from the surface to the center. Yeah, so the drying time or whatever, heating up time will become longer. This is the conventional, or what I would call the conventional heating. In microwave heating, the situation is much different. So first of all, we don't need a hot gas as a heat source. We can have a hot gas, but it's not necessary because the heat is generated inside of the material. so by dissipation of energy from the electromagnetic field. And the only thing that is now relevant for us is maybe the thermal conductivity inside of the material, because we would have the heat generation in the center, I already told you, and then we would like to conduct heat maybe also to the surface or wherever. But yeah, it's independent of the heat transfer coefficient at the surface. The thermal conductivity is relevant only for internal heat balance. I've just said it. And then there can be a decision. So from the engineering point of view, we like to use dimensionless numbers to make decisions much easier, or to not I don't know, invent new models for every problem, but to say, okay, based on a very simple consideration, or based on a very simple formula, I can decide, is it useful or not? And here for microwave heating, so at least to my opinion, one would it be useful would be when the so-called Biot number, which is the relationship between the heat transfer in the surrounding and the thermal conductivity, is greater than 1. And why do I say that? Because if the alpha would be bad, so this means if you cannot transfer the heat through the gas phase to the surface, you could also use infrared heating, because this is the radiation of the infrared would not penetrate too deep into the material. It would just heat the surface, and this would be sufficient to overcome the alpha. But the microwaves, they can penetrate deeper, and they can also reach the core if the lambda, so the thermal conductivity inside of the material, is very low. So that I would suggest use microwave heating when the lambda is small, even if you have a high alpha. And what is the heating based on? I think I don't need to maybe say or explain this too much in detail in this community, but just to maybe recall a little bit. The material property that controls the heating of the material is the complex dielectric permittivity. And since we are using 2.45 gigahertz in our application, I have collected here the dielectric constant and the loss factor for several materials. And what you can see is that water is, with big distance, the best susceptor, so to say. Based on these values, it has a very high heating efficiency, and all the products that contain water to a certain amount have also good heating or microwave heating properties, whereas substances that contain no water, at least at low temperatures, have relatively low values here for the dielectric constant and loss factor, so that the heating properties are usually also quite poor. And this is especially the case, for example, for PTFE, for Teflon, for air, or even for water ice. I have collected here or brought here a diagram from our research. This was measured in cooperation with the MFPA, the Material Forschungs- und Prüfanstalt Weimar in Germany. And here we have measured the loss factor for clay material at the temperature of 25 degrees Celsius, so at room temperature. And we have plotted this loss factor here over the water content of the clay. Yeah? So the clay comes out of the ground, it contains some water. So if we look at the numbers here, it contained at the very beginning 250 grams of water per kilogram solid. And then we dried the clay. So we removed the water, and then we came, of course, to smaller values here of the so-called water loading. And we measured the dielectric loss factor here. And as you can see, for drying, this is very important. The loss factor reduces with the loss of with the removal of water. And what does this mean for process engineering application? This means that the heating conditions become poorer, and that we have to find out that we have to investigate what is then the efficiency of the process, or how can we still transfer heat if we go to very low values of the loss factor. The loss tangent I have also put here for completion. Actually, the loss factor is not maybe the only thing for an orientation. If the heating conditions are good, usually the loss tangent actually is regarded. And this is the relationship between the loss factor and the dielectric constant. And and if it goes towards zero, as for example, Teflon and air, then the material is transparent for the electromagnetic waves, and it's not possible to heat them. I would also like to point out on the role of the temperature. So not only the water content is important for the heating efficiency, but also the temperature. So different materials have a different dielectric constant or complex dielectric permittivity at different temperatures. And we have again measured this for clay at room, not at room temperature, at different temperatures now, and at different loadings with water. You can see here, these are different water loadings. So the upper curve has the highest loading, 200 gram per kilogram, so 200 gram water per kilogram dry clay, and then reduce the water content in this direction. So this, of course, as you can expect, or as you have maybe expected, with the reduction of the water content, we reduce here the values of the dielectric constant, and also, of course, of the loss factor. I had shown this before. But as you can also see, if I increase the temperature, there are some slight changes. Yeah, so the dielectric constant decreases a little bit, and the loss factor increases. And then if we look again on the tangent delta, on the loss tangent, we see that it would increase if the temperature increases. And this again means for a drying process, even if I reduce the water content of the product, but if I increase the temperature at the same time, the heating conditions could still be good enough to also go to very low water content. So this is a very important finding here. And then at the beginning in my list of disadvantages, I already mentioned that the heating conditions depend also on the geometry of the material. We use a very simple formula actually to calculate the penetration depths for the microwaves. We are process engineers. We are not electrical engineers. But this is sufficient to identify at least some behavior. This penetration depth depends on the wavelengths. So it depends on if I use 2.45 gigahertz or 915 megahertz microwaves. And it depends on material properties, again, on the complex dielectric permittivity. So as you can see here from my picture, the 2.45 gigahertz waves, they penetrate less into the material than the 915 megahertz waves. So this means in industrial applications, if I have a very thick material where I would like to bring the heat very deep into the material, I rather choose the 915 megahertz solution, whereby when my material is quite thin and I don't need this high penetration depth, the 2.45 gigahertz would also be sufficient. Due to this penetration depth, or to this limited penetration depth, I had already said before, the temperature field is also, it depends on the thickness of the material. So this is the simplest case and maybe the best case scenario. So we transport the heat to the core. We have here the high temperature, and towards the wall, the temperature decreases. Yeah? So this is a very typical profile. We will see that this, best case scenario, or this a school book image does not apply to all of the industrial applications. But according to this behavior, I had also already said before, we can have local overheating in the center, and if the heat transfer conditions from the location of the hotspot are not well enough, this can have a dramatic effect. So for pyrolysis, it was not that bad actually. At the end, this is the conversion of the wood into a biochar or charcoal was our goal. But for example, for this application here, this is a clay that we have heated up to more than 1000 degrees Celsius, but we can see that the process took place only in the center. The rest of the clay remained almost untreated. And this is, of course, then not a very good process design, because at the end, the product quality is really bad. And what does the penetration depth do in other geometries in what we call thermally thick materials? So this is a facing brick, and actually I brought one here today so that you can have maybe an impression how it looks like. So if you look now on the video, you can see me and you can see this brick. Yeah? So this is a normal brick used for building houses. And this we have put in a microwave, and then we have measured the temperature along this side of the brick, yeah, so in this in the horizontal direction. And for this measurement, we have used a fiber Bragg array, and this I have also brought. I just need to take care that I don't hurt myself with the laser light, and I also put it into the camera. So I don't know if you can hopefully see, or maybe not so easy, that we have now here fiber glass fiber with several points of measurement. So you can see everywhere where the red points are. So at these points we can measure the temperature very detailed along or across quite a long distance. Yeah. So and this we have done. So we have put this fiber into the clay, and we have measured the temperature. And at the very beginning, of course, we had room temperature, and then the clay slightly heated up, and you can see the temperature profile is not as the profile that I'd shown you before. Yeah, it's not like developing like this, but you can see it's heating more on the sides, on the edges. So the temperatures increase here faster. And in the center, it remains cooler at the beginning and only at the end. So after 1 hour, there's some temperature homogenization due to heat exchanges, or maybe even due to a variation of the penetration depth. Yeah. So to simplify this profile here, it looks like this. So we have two hot spots and a cold spot in the center. And this can be problematic for a process, for example, with chemical reaction, or if the local overheating would be much more dramatic than shown here. And what is important here for process control would be, again, to understand how this penetration depth of the electromagnetic waves changes with the removal of water, so with the drying of the material. We have measured this again, or calculated this here for this clay material at 25 degrees Celsius. And you can see it's at the beginning is very small, so I don't know, 2.5 to 5 centimeters here. And when the moisture is removed, then the penetration depth increases dramatically, which means that also the heating conditions change during the process, which would be good in that case, because we would have a better homogenization of the temperature. This can also be simulated. So here I've brought some pictures of some COMSFOR simulation that we have done, again, with the partners from Weimar. And you can see here the electromagnetic field distribution. We don't need to look too much on the details, but what I would like to point out with these images is the geometry is important. Yeah, the facing brick has a different geometry than a roof tile. And the roof tile, if I put it the same way into our microwave oven, so I put it flat on the plate, the heating is much different than compared if I would put the roof tile in this direction. This is related to the penetration depth again. Yeah, so the penetration here would be limited because the waves would come here to the surface of the clay and then would penetrate from here. And if I would put it vertically, so upside down, the penetration depth, or of course the depth of the material, would be much smaller. So this is something that is also, again, important for process design, or for the design of the reactor. And to show you how we do these experiments, I have brought you a picture from our microwave dryer. With a small video here of this facing brick. So this dryer is equipped actually with 2 magnetrons. So we are using microwaves and magnetrons at our institute that come from the side. We have a rotating plate here. You can see, it's also rotating here in the picture. There's also so-called mode stirrer that shall be responsible for homogenizing the electromagnetic field in the cavity. And for the drying purposes, what is very important is that we have a blower, so that we have some air supply, and also some air removal, because we are generating a lot of water vapor and this water vapor needs to be removed from the process room. And then we have different other things, for example, installed a balance, we have fiber optical sensors, IR cameras, we have an online recording, a dew point mirror. This is something that is important to understand how the air humidity or which value the air humidity has, and things like this. Yeah, so this is a microwave dryer that we use for drying purposes. And for higher temperature or high temperature applications up to 1000 degrees Celsius, we have also microwave reactor from the same company, Püchner, Germany. This is equipped with only one magnetron, but otherwise has almost the same thing. So also again, a turntable with a scale, a pyrometer. But here also because of the reactions that take place, it's very important for us that the container is gas tight, that we can supply nitrogen to avoid, for example, oxidation or burning of the material, and things like this. Yeah, so online measurement of the gases and so on. So this is quite a small container. It's 20 times 20 times 20 centimeters high, large. So you can see here, but it's a very special equipment that allows a very specific processes inside it. And I would like to come back one more time to drying, maybe to point out again on why is microwave heating maybe better than conventional heating for drying processes. And I think a very how to say illustrative example is shown here. So what you can see here is again this this facing brick that we have dried, and we have measured the temperature here with a fiber optical sensor. You can see here the cables or the fibers, and we compare here the microwave heating process with the hot air drying process. And as you can see, we applied the maximum temperature for microwave heating was 65 degrees Celsius. So when we reached it, we said, okay, stop the heating. And as you can see here, a little bit the process control. If the temperature decreases again, start heating again. And for the hot air, we applied the whole time 65 degrees Celsius. And yeah, what you can see from comparing these two graphs is that the microwave heating is much faster than the hot air drying. And this time that we, or this time period that we can reduce the process time, this is already an increase of the, or contributes to the increase of the process efficiency. Now, on the other hand, I've plotted here the drying rate. So the gram of water removed per minute and square meter surface area of the material. And this is also interesting because the drying rate increases. I mean, if I have a higher temperature, I can remove much more water within the same time period. And this makes the process faster and more efficient. Yeah, we have compared this now for different clay materials. So for this facing brick, roof tile, and this is another kind of a brick. And what you can see is that the drying curves, this removal gram per water over time and square meter surface area changes depending on the material. And this is not only because there's a slight variation in the loss factor of the material, maybe slight variation of the initial water content. This has also to do with the geometry of the material, with the maximum size of the longest side of the material, and if it contains pores, for example, like this HLZ. This is actually a hollow clay material, which can dry maybe a little bit faster than something that is completely full. So here we are now investigating, first of all, how do the heating conditions depend on the geometry, and also on on how to say on changing also the material geometry, or designing the material geometry to make not only at the end the product quality high, but also to enable a more efficient process. And this is one of my last slides already, but it's very important because it is about the energy efficiency. And I have said microwave heating makes the process faster, and making the process faster means we save energy. But at the end, the energy efficiency of the microwave heating depends a lot on the loss factor and on the water content at the end. And what we have investigated is how the efficiency changes with the amount of water for a drying process. This means, again, I have plotted here this water loading. So this means the water is decreasing again in this direction. And on the ordinate, I have plotted the energy. And what energy have I plotted here? Well, the blue curve is the latent heat. So this is the energy that I need for the conversion of water from the liquid phase to the vapor phase. And this E with this index CAL is the sensible heat. This is the heat that I require to heat the material up from room temperature to the process temperature. So here from 20 degrees Celsius to 65 degrees Celsius. This EuMA is the magnetron power. This is what we have applied to the process, and EREF is the reflected power. This is actually the electromagnetic wave that is reflected and then guided actually to a water a container. So this is the unused power. And and for the efficiency, I calculate actually what I need. The energy that I need is the conversion energy and the volumetric energy, so the energy that I need to heat up, referred to the energy that I have, applied in the process. And here I have even reduced the reflected power to only account for the energy that the material actually sees. And I have plotted this, so you can see here, this is the magnetron power, the purple one is the reflected power, and the blue one and the red one add up for this term, yeah? And what then I've calculated this eta, this efficiency, for the beginning or for still quite a high water content, and the efficiency was almost to the theoretical efficiency of 80%. Yeah, so 80% is usually the number with a 6 hump that one has in mind for the magnetron or microwave heating efficiency. But if I go to lower water content, the efficiency decreases, and this means that I have much more power applied to the material than the material has actually used for evaporation or for heating up. And this decreases the more the water is removed from the process. This is important to understand or maybe to investigate, because if we would like to have a high process efficiency, we would not remove too much water, but in a drying process, we have to go all the way here. And the question is there any possibility maybe to improve this process by, for example, going to higher temperature levels or by applying intermittent heating or things like this? We have also studied pyrolysis of biomass, pyrolysis of wood. So the background is what can you do with a wood pyrolysis? So with the burning of wood in the absence of oxygen, so a little bit different than the fire, maybe that you can do in a garden or in a camp. So this is the heating under nitrogen atmosphere. And this has the purpose, for example, to produce biochar. So this is a charcoal. To produce non-condensable vapors and to produce bio-oil. And the bio-oil later on can be further treated to achieve at the end a fuel, for example, a biofuel for planes or aircrafts or something like this. And this can also be done with microwaves. Why? Because wood at the beginning contains water. Water is a good absorber, so works very well. And we have investigated this for different power application. We have measured the temperature levels that we have achieved, and we have also investigated the mass conversion at different temperature levels. This is from a chemical point of view, was very interesting for us. I think the take-home message is that the microwave cavity is quite a black box, and in our case, it was actually black because all the pyrolysis oils coated the walls at the end of the process. but we cannot access all the data that we need from this microwave pyrolysis experiment in our reactor. So what we have to do is we have to combine the experimental data from this microwave reactor with experimental data that we obtain from another experimental setup. So for example, we could not measure all of this conversion, of this mass conversion, or the exact temperatures in the microwave reactor, but we have done this then in a conventional oven, and we have then measured all the interesting parameters. And by comparing then the mass conversion from the balance that we have installed here, from the weight of the sample with the weight of the sample in this process, we were able to at least, again, roughly correlate the process behavior or the different conversions in the process without having the possibility to measure this in a microwave. And for all other situations where we are neither able to measure in a microwave nor with other setups, so for really unmeasurable data, we use simulation tools. And this is something that we do a lot actually at our institute, is the development of mathematical models, of simulation tools to investigate the processes on different scales. And what is most inaccessible is usually this pore scale. And that's why I've brought here an image of current research of biomass pyrolysis. So you can see here these wood spheres, and we have pyrolyzed them up to different temperatures. And then we interrupted the process, and we investigated the porous structure of this wood spheres here with a X-ray tomograph. It's a microtomograph, as similar as at the doctors, but here with a very high resolution, so that we could image actually the tiny little micropores inside of this material. And this is again important for us to understand how are the transport, heat transport, mass transport conditions on that scale, because this scale is affecting at the end the above scale, the mesoscopic scale, and later on also the macroscopic scale. So all of course is interacting with each other. And that's why we are really taking care here of the details. Yeah, so I'm already at the end of my presentation. I started actually with the formulation of the goal that we are now or currently investigating microwave heating with the aim to contribute to the European EU Green Deal. And this means we are interested in reduction of the process heat. So this means process intensification due to volumetric heating. At the same time, electrification to go from the fossil fuels to renewable energy sources. And microwaves we have chosen here because they have very high heating rates. We are not at the end of the research. There are a lot of things to do. So we need to understand how we can prevent local overheating, for example, with intermittent heating cycles, and how we can also control the energy dissipation for the different geometries that we are treating, particulate material or particle material, solid bulk or on block, or even very volumetric materials, and maybe even to couple this with other technologies. So this is the current research that is going on. And this research takes place in the frame of the CRC bulk reaction, which is in Germany a DFG-funded national research network with partners from different universities. It's the Ruhr University Bochum, it's Otto von Guericke University, it's the Christian Albrecht University in Kiel, and the TU Dortmund. And of interest are high temperature processes that usually take place in really, really big kilns at very high temperatures. So if you would be interested here more into this topic, you can, of course, scan this QR code and visit our website or our LinkedIn profile there. And with this, I would like to thank you for your attention. I would like to thank actually the national funding sources, the DFG, for example, as well as other internationally based funding. And I would like to thank, of course, the PhDs of my research group that are contributing here to the work. Thank you.
Yeah, thank you, Nicole, for this very interesting talk. I think you can keep your slides open for a second. I'm sure there are plenty of questions in the audience. So maybe we can then just jump around a bit if needed. So for all of you who are attending this webinar, you have now the chance to ask your questions to Nicole. You can use either the chat window or the Q&A panel, which you should be able to find on the lower bar of your Zoom window. So yeah, just type your questions. I will forward them to Nicole, and we will be happy to answer. So there have been already a few questions during the talk. So the first one is pretty obvious. Will these slides be shared after? So I think we do not share Nicole's slides, but you can find a recording of this webinar on YouTube in the near future. So we will just edit it a little bit, and then we will notify you when it's back online on YouTube. There was another question. Which technology is the best to address microwave heating applications in a sustainable way?
Yeah, that's a good question. I mean, sustainable, what does it mean? Yeah, so sustainable it's an electrified process, and at least at our university, we are using 100% renewable energy sources. So even either from solar energy or from wind energy. So based on that, we are from the process heat 100% GHG emission free. And then the other question is, how can we meaningful and in a responsible way use this technology, so without spending too much energy that we don't use? And I think this energy efficiency point, this is important, and this depends on at the moment. So designing these processes for microwave heating is now always an individual solution. So if you go to a company, if you would like to buy a microwave heater, each company would sit down with you and find an individual solution for your product. And I think to make this maybe to approach this problem maybe in a more general way, based on knowledge that we would like to gain in research projects right now and in the future, this would be, I think, a sustainable way.
There are quite a few questions in the last minute then. So I'll try to order them properly. What are your experiences, Nicole, with thermal runaways? How can it be predicted, prevented, or countered?
Yeah, thermal runaways are really bad, I would say. How can they predict it? So at the moment, what we are doing is we are controlling, or we are monitoring the temperature. So we are measuring the temperature inside of the material where we already expect actually the highest temperature, the hotspots. And there we put a fiber optical sensor and we measure the temperature during the experiment. Predicting it would be based on a balance between the energy dissipation. I have shown there's a quite simple equation that we used for that. It's based on electromagnetic field strength. It's based on the loss factor. It's based on the frequency of the wave. This is on the one side of the balance equation, and on the other side of the balance equation is the heat transfer from the hotspots into the surrounding. And this is also something that you can predict in advance, because you can measure, for example, the thermal conductivity. And based on that, thermal runaway could be also predicted on a theoretical base, I would say.
Okay, so the next one would be, have you tried varying the frequency during the process? For example, to change the penetration depth as the material dries? Frequency of
right. So, well, what I know from technical experiences is a combination between the solid, for example, a solid state generator and the magnetron. For example, if the solid state generator that works at 915 megahertz and the 2.45 gigahertz magnetron is always technically really demanding. But there are apparatuses that are equipped with both. So based on that, it should be possible to switch on the one and the other and to change the frequencies between 915 and 2.45 gigahertz. So this is something that is technically available. If it will be working very well, I'm doubting a little bit. On the other hand, what you can also do is you can use a very small bandwidth from a solid state generator. So let's say 2.45 gigahertz plus minus 50 megahertz, for example, to vary the frequency in a very small bandwidth. But this can also already change, of course, the penetration depth. And this is also something that is currently studied for different materials as in process engineering.
Okay. Okay, so maybe because I think this fits very well to the previous question, I would skip one and come back to it in a second. I guess it's generally answered, but maybe you can elaborate it a little bit more deeply. Have you generally considered other RF generators than magnetrons, so which are slow to control? For example, a solid state device could give you much shorter heating cycles. Maybe you can briefly tell us what is available in this power regime and what is used in industry.
Yeah, so there are definitely the solid state generators used also in lab scale applications or in larger scale applications. We work together with partners that use solid state generators. For us, the magnetrons were more reliable and I would say more stable. So we have used them in our equipment, but both I think are quite common in our community. So this would be possible. For the power, I now need to lie. For the solid state, I don't know exactly now the highest power that you can apply. For the magnetrons, of course, you can reach also several megawatts, but usually this is not something that is really, how to say, applicable. So we don't need, in German there's a saying, with Kanonen auf Spatzen schießen. So we don't need to shoot with a big cannon on a very small bird. So if we would apply much or a very high power on a certain volume, you remember I have talked about the penetration depths, I've talked about hotspot. This will not be very useful. So what we are doing in process engineering is we are building modular equipment. So this means we have one cavity that has a certain power, then behind it there's another cavity and so on. So we are numbering up actually the cavities, and with this we are increasing the overall power of the system.
Okay. So again, I think we then move away from the generator a bit. So the question then was, thank you for your talk, first of all. How do you deal with changing dielectric properties of the load? So during the drying, for example, do you have an adaptive matching network connected to the magnetrons, or I think to the source in general?
Yeah, so we are measuring the reflected power, and based on that, we can reduce the power. For example, if we are observing that the reflected power would become too high because the electric loss would become too small. So this is something that we could do online or directly during the process, I would say. On the other hand, we are trying to base the whole process control on the model. So we are looking at the change of the dielectric loss factor, how much energy we can absorb at the very beginning, and how this changes then with the progress of drying. But adaptive matching network, in our case, it's more the measurement of the reflected power and then adjusting it accordingly. Or what is also possible is to shut down the magnetrons that we are using for a while and then control the temperature. And if we see the temperature is decreasing, then turn on the magnetrons. So as in a household microwave, this intermittent heating, this is also quite a good option, actually.
Okay. So then there are two more questions right now. The first one is, I think, very, very general. So what are there technologies other than infrared or microwave for drying?
Yes. Yeah, so there's hot air drying, for example, there's contact drying, there's superheated steam drying, there's even how's it called? Plasma drying. Things. So it's not called plasma drying, but I don't find the word right now. Supercritical drying is actually the word for that. So there are many different options for drying, yeah. I have just focused here on one technology.
And currently the last one, how does the material hold up the drying process? How susceptible are the materials to the EM radiation? I think that rather depends, right?
How does the material hold up the drying process? I don't understand this question, but how susceptible are materials to the EM radiation? Yes, they are, of course. If they contain water, then they absorb a lot of energy.
I think this is a critical point. You need the water content, right? Not only for drying, but also for the other heating, for pyrolysis. There should
Yeah, of course. Yeah, of course. So at the beginning, we use the water content usually in our products. And when the water is removed, then usually other phenomena take place. So there's like this ionic polarization or even electrical conduction. So this is also here a transition from the electrical point of view from one phenomena to another phenomena. So this is also not fixed, I would say, or not only based on the water content.
Okay. Yeah, so I really liked and appreciated this lively discussion. That's really neat. So if there are further questions, just give me a hint right now. Otherwise, yeah, I would like to thank you, Nicole, for this very interesting talk. And I think we've seen from the discussion as well that it was really interesting, yeah, to all participants in the audience as well. Yeah, thank you for being here, and good afternoon to all our participants. Bye-bye.
Yeah, thank you for the invitation, and thank you everybody for the discussion. Bye-bye.
Bye.